Okay, welcome back. This is now 4.3 and we're still working with direct proofs. Now we're working with rational numbers. Okay, so we'll need some new definitions and we'll work with those definitions in the same way we worked with the even and odd definitions in the previous section. Okay, so the definition for a rational number is the following. R is rational if and only if it's basically the ratio of two integers where the integer in the denominator is not zero. Okay, so R is rational if there exists integers A and B such that B is well, let's say such that R is equal to A over B and B is not equal to 0. Okay. In the beginning, the problems are pretty simple, and it's almost like it defies any sort of sense of your intuition as a student regarding homework. The question will ask, rewrite this as a ratio of integers. So right now, the negatives in front, you need to incorporate the negative so it goes into either the top or the bottom. And that was one of our axioms in the back of the book, one of the T axioms. So you can rewrite that as negative 35 all over 6. Okay, so technically I guess this isn't a ratio of integers when it has this negative thing floating out in front. You have to rewrite it like this. Okay, and in the book and the axioms, that's like T12. You're allowed to do that. So those are pretty easy. Problems that have repeating decimals in them, where you have to rewrite those things as fractions or ratios of integers. Those probably aren't as familiar with, you're probably not as familiar with this kind of problem. It's you could do it if you took Calc 2, right? We give you methods for doing it there, but are there other techniques such that a person doesn't need calculus? And yes, there are. Basically, what you want to do is multiply this number so that there's a cancellation with the decimal part. Okay. So if you multiply this number by 100, so if you take this thing and multiply it by 100, it's going to move the decimal place 2 places to the right. So you'll end up with 37.37 repeating. Okay. And then if you take that number and subtract away the repeating part, so if you take this number here and then subtract away this number here, you'll end up with 37.37 repeating minus 0.37 repeating. Okay, so these parts will cancel out and you'll be left with 37. Okay. So why would I even care about doing that? What does that tell me? You could set it up like an equation. You could say, all right, let's let x equal 0.37 repeating. And then consider what happens when you multiply 100 times x and subtract away plain old x, right? Well, that's just the computation that we did over here. Okay, this thing right here should be equal to 37. Okay, so you can put 37 on the other side, and what you have is an equation that you know how to solve, right? You could solve it for x. So 100 minus x is going to give you 99x. The other side you have 37. And then you have to divide both sides by 99. And you get 37 99ths. Okay, so it's a clever kind of way to produce a fraction from a decimal. Usually in grade school and everything, you're always going in the other direction. You're going fraction to decimal instead of decimal to fraction, right? But these kind of problems, basically you just have to figure out how to multiply the repeating decimal part by some sort of integer like 100, 1,000, such that when you do this subtraction, all the repeating parts cancel out. And it could be kind of annoying if they give you something that's kind of weird, like 3.21352 repeating or something like that. Then it's a matter of kind of how do I multiply this thing to produce that cancellation of the repetitive part. So you would have to multiply by 10, 100, 1,000, right? So if you multiply this by 1,000, you would get 3, 2, 1, 3, 5, 2, 3, 5, 2, right? Repeating then. And then you could subtract away the 3.21352, and you get what you get then. So this would be 130.123, and you could go from there, right? So it'd be 1,000 x minus x equals 3210.31, and then this would be 999 x equals 3210.31, and then you want to get rid of the decimals when you're writing it as a ratio of two integers, right? So maybe multiply both sides by another 100 to produce this. So just moving that decimal place over, and then finally you can divide. And you could always check on your calculator to make sure you're getting the right answer. And it's just, you just have to be good at kind of lining things up and producing cancellations. It's kind of neat party trick. Anyways, one important part in these proofs that we'll be worrying about is the zero product property. We'll be multiplying fractions together, and you need to ensure that when you multiply the denominators, you don't inadvertently get a zero in the denominator. And usually that will follow from the zero product property, which we're all familiar with. It just says if neither of two real numbers is zero, then the product is also not zero. Okay, we're more familiar with it in its contrapositive form, and if you look at number 8, they'll have you kind of figure that out. So number 8, first they want you to write it formally. So write. Stupid pen is still. Write the zero product property formally. Okay, so for all a comma b in the real numbers, if a does not equal 0 and b does not equal 0, then a times b does not equal 0. Okay. Part B, write the contrapositive. So remember, with the contrapositives, you're not messing around with the quantifier or the domain. It's just a matter of swapping the implications parts and negating them. So you're going to make this the conclusion, and this is the hypothesis, and you'll negate them. You'll switch them and negate them, right? All right, so let me get this other color pen back. So for all a comma b and the real numbers, if instead of a, b not equaling 0, now we have a times b equaling 0, then and then when you negate this and part here, by De Morgan's it will turn into an or. So then either a equals 0 or b equals 0. And this is usually the form that they'll give it to you in the algebra classes. Right, so you're probably more familiar with that form. If a times b is 0, then either a is 0 or b is 0, and we use that to solve equations all the time. Right? Okay, so we're going to be proving general kind of statements about rational numbers. Like, are their products rational? So are they closed under multiplication? Are they closed under division? What have you? So section 3, I just sort of label this as proving stuff being irrational. Proving something is in Q. So that's the symbol for the rationals if you hadn't figured that out yet. So I do it pretty much the same way as we've been doing the direct proofs. I'll write out the statement formally, and then I'll write my supposition. Invoke definitions to instantiate. Use all your rules from Appendix A. So there's a lot of rules for working with fractions already sitting there in Appendix A. Show the results have a form of a rational, and that's usually where you end up having to use the zero product property. Okay, and then the conclusion usually follows. Alrighty then, so let's try one, and this, it's the proofs of the obvious kind of thing. This is number 11 in the book. Prove every integer is a rational number. Okay, so first translate that into symbols for all n and z. N is rational. Okay, so for all numbers, if the number is rational, for all numbers, and if the number is an integer, then it is rational, if you'd rather do it as a universal conditional. Okay, so suppose, do our supposition, suppose n is a payback integer. Okay, then we can invoke our definitions, right? So, well, we don't even need to do that. We can just say something like, from our knowledge of arithmetic, n equals n over 1. Okay, where n is rational, or sorry, n is an integer. 1 is a non-zero integer. And thus n is the ratio of two integers where the denominator is non-zero. And then by definition it must be rational, right? So by definition it is rational. Okay, I struggle a little bit with this one because this factoid up here is really not to be found. I couldn't find anything in the axioms, and you really need that fact to unlock it. If you can't do that, then you really can't do anything. And it might follow from the fact that it may follow, and I don't think it's going to be a problem, but you may be able to engineer this from the fact that n is equal to 1 times n, which is equal to 1 over 1 times n. But even then, it's like it's kind of iffy, you know, and sadly, I don't think they give you enough in the book to really make this conclusion that n is equal to n over 1. But sometimes, like I said, it's just so obvious. Unless you're rebuilding all of the foundations of mathematics, you're going to have to assume something, right? I don't know. Okay, so let's try another one. I would just wanted to do that one because of that little fact, you know. Don't get hung up on some of this stuff. It's not worth it. You could spend your lifetime really researching the foundations of mathematics, and a lot of people did at the beginning of the century. So don't be one of those people. You're just going to be reinventing the wheel and not even know it. And then it's like you do all this research, and you could literally get a job in your spare time, do all your research and the foundations of mathematics, spend your whole life doing it, and not get as far as the people who spent their lives doing research in mathematics in that particular field at the beginning of the century, because that's all they did. That was their job. They were like professors and stuff like that. So it's kind of like, just don't get hung up on it. So anyways, in my opinion, I mean, I did get hung up on it, so maybe that's why I'm kind of jaded. Anyways, the product, we're trying to prove the product of any two rational numbers is a rational number. Okay, so for all r comma s in the rationals, r times s is rational. Okay, so suppose r and s are payback rational, and then we're going to invoke kind of instantiate them into their fraction form using the definition. Okay, so by definition, there exist integers, and we need enough integers for two fractions, so we'll say integers a, b, c, and d, such that m or r is equal to a over b, and we'll let s be equal to c over d, and then we also have to make sure the denominators aren't 0. Okay, so where b and d are non-zero. Next, we'll consider where we want to end up, right? So consider what is r times s, right? So consider r times s, and by substitution, that's equal to a over b times c over d. Then we can multiply these out using the axioms in the back of the book. So that'll be a times c over b times d, and that's axiom T15. Okay. And then that just equals, AC over BD. and then we make a note about this, right? We want to say that AC is an integer, BC is an integer, and BC is not zero. AC is an integer, BD is an integer, and BD is non-zero. So we note AC and BD are products of integers and therefore integers. Okay, because we know from the last section that the integers are closed with respect to multiplication. Also then, and this is where we use the zero product property, B times D is the product of two non-zero integers and is therefore non-zero by the zero product property. Okay. Hence, by definition, it's rational. Which is what we wanted to show. Okay. I'll just end it there. Okay, let's do one more, and then we'll kind of look at corollaries. So 15, or maybe it's 18. If R and S are any two rationals, then R plus S all over 2 is also rational. Okay, so first put it into formal notation. If R, for all R comma S in the rationals, R plus S all over 2 is also in the rationals. And I apologize, I sometimes write S's like this, but I also write the cursive form like that. Okay, those are my S's. Both of them are supposed to be the same. It's just, sorry about that. Alright, so anyways, let's start with our supposition. So suppose R and S are particular but arbitrarily chosen rationals. So we could say by definition of rationals, there exists A comma B comma C comma D with B and D non-zero. So just definition of rationals, we're trying to rebuild R and S such that R, what the heck are we doing? We're trying to add them together eventually. So R's we'll say is A over B, and S we'll say is C over D. Okay, I guess period. We consider the thing that we're trying to prove is rational, so consider R plus S over 2. And then we could do our substitution. So R is A over B plus S, which is C over D over 2. So just by substitution. Then we could say this equals, and now we have to kind of go to our axioms, the T axioms in the back of the book. So this will be AD plus CB all over BD all over 2. And I think that's axiom T14. And then there's axioms for dealing with these complex fractions, and that is basically just by multiplying reciprocals. Okay, so you'll end up after that process with 2 times BD, because I have to multiply this thing by the reciprocal of 2, so that would be times 1 over 2, and then you would end up with just this 2BD in the denominator. Okay, so that's axiom T16. Then we have to say that this thing is a rational number. Okay, so it's going to follow from the closure of the integers, right? So where AD plus CB is the product, I guess, slash sum of integers, and therefore an integer, and 2BD is a product of non-zero integers, and thus a non-zero integer by the zero product property. Okay, thus the thing we ended with is rational by definition. So thus S plus R, or whatever it was, R plus S over 2, is a rational by definition. Okay, so hopefully you appreciate there's kind of a form to it, right? So we begin by kind of rewriting the given variables in rational form as ratios. Then you're kind of looking at the thing that you're ending with, that you're trying to prove is rational, and then you're using the axioms in the book to build a new version of the rational number, and then you show that that thing is the ratio of integers where the denominator is not 0, and usually you have to say something about the zero product property, and then you conclude by definition this thing is rational. Okay, so the last part then is using corollaries. So when you do math, you take all this stuff for granted. And why can you take it for granted? It's because people have kind of beaten all this stuff to death, right? And you would never go through all that. You would just kind of say, well, we know that this is already true. We know that the ratio, the product of rational numbers is another rational numbers. We don't have to go back and reinvent the wheel. So in those cases, what we're doing is really using corollaries and deriving new math from old math. Okay, so proving from definitions, you're working from the ground up, right? So if you're proving from definitions, you're truly just working from the ground up. Corollary, I need to be a little more careful about how I define that. A corollary is kind of a theorem that just directly follows from your proof. Okay, so it's a statement that can immediately be deduced without much work. From a theorem. Okay, and you'll see more and more corollaries popping up as you go through more and more math. if that's what you're going to do. Let's look at deriving a statement from corollaries. This is 25. If R is any rational, then 3R squared minus 2R plus 4 is also rational. Okay, so what they want you to do are use the previously established theorems in order to get this thing as a theorem or prove it to be true. So they list the theorems that you can use. It's let me see what it says. And the book, this is 25. If R is a rational, okay, so use theorems 4.3.1, 4.3.2, and the result of exercises 12, 13, 14, and 15 to derive the statement. Okay. We just did a couple of those exercises, so this shouldn't be too difficult. Anyways, rewrite it in formal notation for all R and Q. 3R squared minus 2R plus 4 is also in Q. Okay, so the first thing I'm going to do is kind of prove that the pieces and parts are rationals. What do I want to do? So suppose R is a rational number. We note these other guys, these other pieces like 3, -2, and 4 are rationals because of theorem 4.3.1, which says that every integer is a rational number. Okay. So I don't have to reprove that each one of these guys is a rational number. Okay. I think that was also exercise 11, where I don't think it's, yeah, okay. Anyways, what else? Also, R squared is rational because of exercise 12. Okay, so number 12 says the square of any rational number is rational. So I'm trying to build to this 3R squared minus 2R plus 4. So the next thing I'm going to do is say that thus 3R squared negative 2R are rational because they're the product of rational numbers. Okay? And that's problem 15. The product of any two rational numbers is a rational number. And then finally you want to start adding things together, but you can't add all three at a time because there's no theorem that says the sum of three rational numbers is a rational number. All we have is the sum of two rational numbers is a rational number, and that's 4.3.2. So I have to build to the sum of these three numbers. So firstly, I note 3R squared plus negative 2R is the sum of rationals and therefore rational. And that's, I think that was one of the theorems, theorem 4.3.2. Then I could say, because I know this guy is rational, I can add it to 4, which is rational. So I'm only adding two things. Okay. Secondly, then, 3R squared plus negative 2R plus the 4 is the sum of two rationals, and therefore rational. Okay, and of course I have to say which theorem. That's again by theorem 4.3.2. Okay, then that's it. I got it. Hence 3r squared plus negative 2r plus 4, which equals 3r squared minus 2r plus 4 by some axiom in the back of the book is rational. Okay, so it's a bit silly, but you have to be careful. So the thing that will come up if you take like an abstract algebra or something like that, you'll be given things like a plus, like the associative law, right? So a plus b plus c equals I don't know, a plus b plus c, and you want to show that this holds for I don't know, maybe this isn't the best one. You want to show that that's true for something a little more like a plus b plus c altogether plus some other d equals a plus b plus c plus d, right? Does this second fact necessarily follow from this first fact? You know, if you have a theorem that says that they're talking about three numbers, can you then deduce that actually it works for four numbers? And usually you'll have to prove that kind of stuff by induction. So it works for all sets of finite numbers. Okay, and that can be a bit tedious, and it's not something I'm all that good at. But those kind of problems are out there, and you just have to be aware that sometimes you're being asked to prove the obvious, you know, and it's hard. Don't try to reinvent the wheel. You know, don't get too carried away with it. Like I said, people in the beginning of the century really spent a lot of time developing the foundations of mathematics. You'd go back and read. Hopefully, somebody has like a Cliff Notes version of all that stuff somewhere. But I don't know. Anyways, that's it for this section. We'll leave it there, and we'll see you next time. Okay. Bye bye.